Welcome back to some more geometry. Today we are talking about proving segment relationships. So we're going to be seeing how we can show that, hey, these segments are related without actually taking out numbers, without having to have numbers. So let's kind of look at some basics real quick. So there's the ruler postulate. We don't use this very often, but what it's saying that at wherever you're measuring, one point we'll denounce that R0, and then the other point will be whatever we're measuring out to. In this case, it is 4 or 4 inches. So this, we can say that's 4 inches long. That's just a postulate that's created to state the obvious, if that makes sense. But let's kind of look at the one that you'll be using a lot. And this is called our segment addition postulate. Segment addition postulate. So this segment addition postulate is a pretty powerful postulate because it says that, hey, if I have two small segments, so I got segment AB, remember it takes 2 letters to name a segment AB, and segment BC, and they happen to be on the same, they're all collinear, I can connect them and make a whole new, longer one segment called AC. So kind of get rid of that B in the middle, and we connect it as one. So if you have A, B, and C on the same, are they collinear, and B somewhere between? Now, it doesn't have to be in the middle, it just has to be in between. So that means that I can add the 2 smaller segments, AB plus BC, and create a new segment AC. Now, that's a great one because you can show how you can combine them to make one. It is now, whatever the values were individually, they're actually now that value. So, for example, if this was 3 units long, this was 2 units long, this new one is now 5 units long. It didn't change how long it is for the 2 of them. It just combined them to make one. But this postulate also works the other way around. You can say, hey, I have this long postulate that has a point in the middle. I can split that up and say, hey, that long postulate is made up of 2 smaller ones, A, B, and B, C. So it works both ways. That's what the if and only if means. If only if means, hey, it works forwards and backwards. You can put them together to make a big one, or you can split it apart. Take that big one, split it apart. Okay, these next 4 properties are also used a lot. I'll take that back. It's not used a lot. This one is. Definition of congruence is used a lot. These 3 have to be stated because we would use them later. So reflexive property real quick means that, hey, this is the same thing. The same thing equals the same thing. So DE is congruent to DE. You mostly say that right before. So this kind of goes to that. You say this right before you add or subtract them from a segment. So they usually say that before you do that. Now, symmetric property, all that lets you do is just switch the position of what comes first for, like, aesthetics purposes. Like, you know how we usually solve x equals something? In problem 14 and 3.4, we had 1.25 when we worked it out equals x, and then they switched to say, hey, x equals 1.25. And you're like, hey, why? Like, what was the reason for that? It's aesthetically pleasing. You know, the proper way to do things is to put x first. So that's called a symmetric property, where you're able to just switch what comes first. The transitive property is a lot like a law syllogism that we used earlier in this chapter, where A is congruent to B, and that B is congruent to C. So if A is congruent to B and B is congruent to C, then A is also congruent to C. It's kind of like it's just showing the relationship between all 3 of these right here, the individual ones. Now, our definition of congruency, that's the word we've been using. This book kind of changed it a little bit. They sometimes say definition of congruent segments. So they kind of write that. They made it individual, but this definition of congruence works not just for segments, but it works for angles and it works for shapes. That's why we just say definition of congruence. It's a lot easier instead of trying to make it unique. That's why I won't be mad if you say definition of congruence segments or if you use definition of congruence. In the book, sometimes they actually shorthand it and say definition of, they use the congruent symbol and they say segments, congruent segments like that. So they'll use the symbol instead of the word. That's okay too. That all means the same. But all the definition of congruence is saying is that, hey, things that are congruent are also equal. Now, the reason that matters and things that are equal are also congruent. So the reason that matters is when things are congruent, we're just saying they're the same. We don't know their values. We don't know what numbers represent what. We just know these 2 are the same. But if I say, hey, CE is equal to FE, then we're saying the actual individual values also equal. I can manipulate this. So it's like saying this, 5 is the same as 5, right? Well, 1 plus 4 is equal to 3 plus 2. Now, it's still 5 and 5, but now we look at the individualness. We can manipulate numbers if we need to solve for this. Or let's say something like 1 plus x equals 3 plus 2. Now I can be like, oh, well, what's x? I can then I can move numbers, subtract, I can add. We have to switch things to equal before we can do that. So let's do two problems together. First problem here. Sorry. In blue, we're going to do it in blue. In blue, it says that CE is congruent to FE, and then it's ED right here. This part of the segment is congruent to this part of the segment, EG. Okay. The goal, what we're trying to prove, is that the entire thing is equal to the entire thing. So in our heads, we say, well, yeah, they're the same. You know, if I put the two parts together and put these two parts together, since these two are equal and these two are congruent, they're congruent and congruent, then it has to be the same. Well, let's prove that. That's what we're trying to prove. So we always start with our given. Whatever written in the given, we always put that first. So we're going to say CE here is congruent to FE, and ED right here is congruent to EG. Okay, so that's given information right there. Right, and if we look right here, all they did was switch those to equal. So that's our definition of congruence right there. We then look at this part right here. They're actually going ahead and say, hey, what if I put CE and ED together and make a whole new segment called CD? Remember, that's our segment addition postulate right there. So when they actually combine two smaller segments to create a whole new one, that's our segment addition. But that didn't happen on 4 right here. What happened is we look at the information we had above. We say, hey, those are equal and these are equal. They just switch those out. What's the fancy math for switching things out? It's our substitution. Now, they did create another segment addition. As I said, segment addition. So if we already combined one segment right here, let me clear that out. It's kind of congested right there a little bit. Let me erase that. Come on. Anyways, since we already created a new segment CD, remember the goal is to get FG. So then we're going to have to go ahead and create FG by combining those segments. So remember, FE here, FE plus EG is equal to the entire thing FG. That's our segment addition postulate. Now, there's another substitution going on. So the goal, remember, is ultimately to get CD on one side and FG on the other side. So we're looking at 5. We already got FG. Well, above, we said that those exact same individual segments also equal CD. So by substitution, we're going to plug that in there. We're going to say CD is also equal to FG by substitution. Now, all we did right here is switch that from equal to congruent. So that will be our definition of congruence. And that's it. That's that one. All right, in class, we did this one together. Or actually, I'll let you guys do it. So if you guys missed it, go ahead and pause it and then try yourself. But hopefully you did try it. Now, we look right here. We got K is the midpoint of GJ. H is the midpoint of GI. So the goal is ultimately to say that this individual segment and this individual segment, that's what we're trying to prove, are congruent. Now, in the given, we know the entire thing's for sure congruent, and we know that these are the midpoints right there. So we start with the given right there, given. All right. Next thing right here, since we know K is the midpoint of GJ and K and H is the midpoint of GH, we can say these statements right here. These statements say what? That those are equal now. It splits in half. So we had that conversation about what exactly is this? Is it definition of midpoint or midpoint theorem? So by their actual meanings, this is a midpoint theorem. Midpoint theorem. I won't be mad if you put definition of midpoint theorem, because definition of midpoint's similar, but definition of midpoint say they're equal. Midpoint theorem say they're congruent. So now though, they went from here to here. Now it's not definition of midpoint. I know it says it's equal, but all they did is just switch out the congruent to equal. Remember, that's our definition of congruence. Congruence right there. All right, so looking ahead, We're number 4 now. So it says GJ is congruent to GI. Well, what is that? Well, remember, that's also up here in the given. So it's okay to split the given depending on what way you kind of go about this problem. Ours was a lot more simple than this one. So we're going to just call this given because it's in the given. And then they did the same thing kind of above. They changed the congruent to equal. That's our definition of congruence. Somebody asked the question, can you write the same thing multiple times? Yes, you can. It's perfectly okay. If that reason works for what's going on, then yes. All right, moving on. We got CJ is equal to the 2 individual parts in it. So just like the last one, it took the 2 parts and put them together to make a new one. Here, we're kind of splitting it apart. We know GJ exists, and we know those 2 parts that exist inside it. So still the same theorem. I mean postulate. It's a segment addition postulate. If you remember, okay. And they did it twice. They did it for this side GJ, and they did it for the other side GI. Now above we had GJ and GI equals, and we know those 2 individual parts equals the 2 smaller ones. And all they did from 5 to 7 is they substitute. They took both of these and put them in place of GJ, and they took both of these and put them in place of GI, right there. So that's our substitution right there. But then what happened again, y'all? What happened again? Right here and right here. Remember, up above, we said those parts equal. They substituted again, and they kind of switcheroo on us right there. All right, so yes, you can have the same statement twice, back to back. Totally okay as well. That's why I give you this example right here so you can see those things are possible. All right, so they actually went ahead and put them together, or also what's a fancy math word for put it together? Addition. They added them together. They got rid of the 2 on both sides by division, and then ultimately they switched it to congruent. That's our definition of congruence. So hopefully this helps. Make sure you look at both of them, have both of them down, because both of these examples are really good to look at while doing your homework because they are similar to that. So lots of the steps are very similar. Hopefully that helps, y'all. Bye.